Okay, we have seen moments denoted by mu1, mu1 dash, mu2 and so on, mu2 dash, mu3, etc. We have seen density functions fx. Now we will see moment generating functions. Now we have two types of distributions: discrete probability distribution and continuous probability distribution. So we define moment generating function MGF for both discrete and continuous probability distribution. Better to write it in small letters. So MGF for discrete probability distribution for a variate x, we know this variate x, at or about x equal to a, not at origin, at x equal to a, is given as, this is our probability, ith probability, into e to the power t xi minus a. Okay, so from this definition you can understand that we have the moment generating function for the discrete probability distribution for variate x about x equal to a as the expected value for this e to the power t x minus a, and is given as this thing. Clear? This is for discrete probability distribution. Similarly, for continuous probability distribution, we have, you know this very well, we have done this for density function. This is this e to the power t x minus a, this into fx dx. So this is our moment generating function for continuous probability distribution. Clear? Note it down. Note it down in your book, and then I'll proceed further. So what have I written? I have written like this. This is equal to pi e to the power t xi minus a. Small a or capital A, whatever you want to use. If you expand this, this is e to the power something. So if you expand this exponential function, what you will get is, expanding, first will be pi, then second will be t into summation, this is pi into xi minus a. This is what you will get. T will be out, and then this, then t square by factorial 2 summation pi, this is xi minus a, not capital A, we are using small a. So this square, so on. When you reach to the power r, you will get t to the power r by factorial r. This is pi into xi minus a into r plus so on. Now if you look at this closely, what are these? These are the moments. We have seen the moments when we were studying, you know, moments in statistics. If you are not familiar with it, go back to that video and understand what moments are. So these are basically, this is the first moment, this is the second moment, and so on. About a, x a, not about origin, about a. If this a is, if a was 0, then this would have been for about the origin. This would have been about the origin. So this is actually pi plus, this is t into mu1 dash, why dash, because this is x is equal to a, this is about x equal to a. Then this is t square by factorial 2 mu2 dash, this is mu2 dash. You go on, and then you have t to the power r by factorial r, and what is this? This is mu r dash, and so on. So we are actually, this function is actually generating moments, first moment, second moment, third, fourth, fifth, and so on. Therefore this is called moment generating function. Okay, and now what I am doing from here, this is applicable to both the discrete and continuous probability distribution. Clear? Note this down, this is very important. Now we saw that the coefficient for t to the power r by factorial r, what was the coefficient? This was mu r dash, this was the coefficient. We get from here that if you take d by of this function ma t, rth derivative, if you take, sorry, t to the power r, if you take the rth derivative of this moment generating function, you get mu r at t equal to 0, or you can write like this also, t equal to 0. So this is a very important formula. From here we will be able to derive mu1. How? Mu1 dash will be equal to the first derivative, dt of mat at t equal to 0. Similarly, mu2 dash is equal to d2 by dt2 of mat at t equal to 0, and so on. So this is a very important formula, and we know how mean, this is mean, how mean, standard deviation, mu2 dash, if you remember, this is equal to, no, mu2 dash minus mu1 dash square is equal to mu2, which is actually our variance. I am writing here, variance is mu2, which is equal to mu2 dash minus mu1 dash square. So these are the formulae that you get in your statistics moments chapter. So I advise you to go to that chapter and revise it. So what I want to tell at this point is that if we have the moment generating function, we can take its derivative with respect to t, and equating t equal to 0, we can have the different moments about x equal to a, mu1 dash, mu1 dash, mu2 dash, and so on. And from here we can get the mean, we can get standard deviation, variance, and all sorts of statistical parameters that we want to achieve. Clear? One more thing is very important. See, we have written mat equal to pi into e to the power t x minus a, or we can write it like this, pi into e to the power minus at into e to the power tx. Now this is a constant, you see, this a is constant, t is constant, we can take it out. So this is actually e to the power minus at sigma pi e to the power tx. But what is this? This is the moment about the origin, a equal to 0. So this can be written as e to the power minus at m0t. So this is another very important derivation that you should keep it in mind, because if you have this value and you have this value, you can get this, or any two of the values if you have, you can get the third value. Clear? Now we have a very standard question for moment generating functions. If you are doing engineering, or you are doing a course in computer applications, or you are doing a bachelor's in science degree, most of the questions that you will find in your semester examinations will be like this only. You will be given a function of x, and you will have to find m0t, that is the moment generating function at origin, or you will be asked to find mat at some value, a will be given, and you will have to find mean and standard deviation, variance, and also the question pattern will be very fixed. You have to understand how we do that, and for any function you can apply the same rule. So we have to find m02, mean, and sd. Let's see how. Very simple. Moment generating function, this is a continuous distribution function. So this will be equal to minus infinity to infinity, this function, into e to the power tx dx, txy, tx minus a, we have tx minus a, but a is 0, we have to find about the origin. So this is the formula for MGF. Here minus infinity to 0, this is not defined, it is defined from 0 to infinity, we have values from 0 to infinity only. So this will be 1 by c, I am taking it out, e to the power minus x by c into e to the power tx dx. Okay, so this is 1 by c, 0 to infinity. What is this? This is e t minus 1 by c x dx. You know very well how to integrate this. This is 1 by c e to the power t1 minus c x by t1 minus c, 0 to infinity. So for the infinity part, what we'll take it as 1 by e to the power infinity, that is 0, and for the 0 part we'll take 1. So this is minus. So what we'll have minus 1 by c into, now I'm taking it up, c minus tc minus 1 or ct minus 1. So this is minus, c cancel, so this becomes 1 minus ct to the power minus 1. Okay, so we have found the moment generating function. Clear? You have noted this down? Let's expand it, because we find values only when we expand it. We have seen it in the definition only. So this comes to 1 minus ct minus 1. Now we have seen expansion of 1 minus x to the power minus 1. You must have studied this in your 11th class or 11th 12th class. What is it? If you expand this, it comes to 1 plus x square plus x cube and so on. So this is 1 plus ct plus c square t square and so on. Okay. So we have got our moment generating function. What we have to find? We have to find mu1 dash, that is the mean, because this is about the origin only. So this will be mean. What is it? It is the first derivative of m0t. This is basically m0t at t equal to 0. So you take the first derivative, this is 0, this is c. C plus 2tc square, 2tc square and so on. Every term after this will have t, and we have to take at t equal to 0. When you put t equal to 0, this is c. So our mu1 dash, that is mean is c. Clear? Now I will take the second one. Mu1 dash is c. Then mu2 dash is given by the second derivative at t equal to 0. Now you have m02 here. This will be, so we have rubbed the first derivative. Let's take the first derivative. It was c plus 2t c square. Then here we have c cube t cube. So this is 3t square c cube and so on. The second derivative will be, this term will be 0. This term will be 2c square plus this will be 3 to 6 at t equal to 0. So this is 2c square. So we have got the value of mu1 dash, mu2 dash, and this is our MGF. Mean, I have told you this is mean. Now you know that mu2 is equal to mu2 dash minus mu1 dash square, and this is our variance. What is this? Mu2 dash, this is 2c square minus mu1 dash square, so c square. This becomes 2c square minus c square, that is c square. Therefore standard deviation, that is our sigma, is under root mu2, that is c. So we have mean as well as standard deviation as c. Clear? This is the type of question that you will be asked for moment generating functions.